everybody. So in today's lecture, I just want to give you a brief overview of acids and bases. Okay, we only have time to go over a few concepts, but it's important to know a little bit about these because you'll encounter them in a lot of different science classes. So what I want to focus on today are some basic definitions. So how do we define acids and bases? A little bit on naming, so you're a little familiar with them. And then I want to talk about what we mean by pH and how that relates to various acids and bases. Okay, so let's start with just some basic characteristics, and you're probably familiar with these. So acids and bases, they both form ions in solution, so they can conduct electricity. Acids turn litmus paper red, bases turn litmus paper blue. Acids have a sour taste, so something like vinegar is going to be sour tasting because vinegar is made up of acetic acid. Bases have a slippery feeling, so it's that feeling when you have soap in your hands because soap is a base. All right, they can react with each other to neutralize and form a neutral solution. And then acids react with active metals to produce hydrogen gas. So remember those single displacement reactions where H2 was a product? That's what we're talking about there. Okay. So let's move on and talk about some definitions. Now we're going to start with sort of a specific definition and move to ones that encompass more examples. So the first definition are Arrhenius acids and bases. And if you're a biologist, this is pretty much what you're going to be talking about. Okay, because this is what most acids and bases that we would deal with in biology would be. And it's pretty simple. Acids are things that in solution, so in water, they are going to release a proton, and bases are going to release a hydroxide ion, okay? And then we just name them. So here we have chlorine, so it still gets the ick, and then we just put a hydro. So hydrochloric acid, hydrobromic acid, and here we have nitrate, that's that polyatomic ion, and so that becomes nitric acid. If it was nitrite, it would be nitrous acid, okay? And then bases, it's pretty easy, the metal and then hydroxide. Okay, so that's one definition. But unfortunately, when we move into chemistry and we're dealing with a lot more compounds, we realize that they don't all follow that particular rule, so we have to broaden our definition. So in chemistry, we're going to deal with Bronsted-Lowry acids and bases predominantly. And an acid is any compound that can donate a proton to an appropriate acceptor. And a Bronsted-Lowry base is a compound that can remove or accept a proton from a Bronsted-Lowry acid. Okay, so notice what this means is we're now kind of talking about these in pairs. Okay, so we're talking about the transfer of a proton from an acid to a base. So if we look at this equation above, we have hydrochloric acid, and here's sodium bicarbonate. So this is an acid because it can donate a proton to the sodium bicarbonate and form our H2CO3, or carbonic acid. And so what this means is the HCl is an acid because it's donating a proton. The sodium bicarbonate is a base because it accepts the proton. And then you actually, on the other side of the equation, have what we call a conjugate acid and a conjugate base. All right, that's all we're going to say about that. I wanted you to kind of hear that. But if you take more chemistry, you'll probably do a lot more with these types of reactions. Okay, and because we're transferring a proton, we can also classify our acids based on how many acidic hydrogens there are. So how many protons can actually be transferred. So monoprotic just means one. So here are monoprotic acids, hydrobromic, hydrochloric, one hydrogen. And polyprotic is going to be able to transfer more than one. So carbonic acid can actually transfer two protons. Phosphoric can actually do three. Okay. All right, and then our third definition, actually, we have to completely get away from talking about protons. So again, in chemistry, where you're dealing with a lot of different compounds, there are some that act as acids and bases, but they don't have that form. So a Lewis acid is the broadest category, okay? So the way this works is if something is a Bronsted-Lowry acid, it automatically is a Lewis acid. But a Lewis acid is not necessarily a Bronsted-Lowry acid. Okay, I don't know if that see if that makes sense. So here's an example. So a Lewis acid, instead of talking about protons, we're talking about what happens to the electrons. So if you note down here, we have H3O. So here's our hydronium ion. It can donate a proton. So it's going to donate a proton to the OH to make water. Okay. And at the same time as it's donating the proton, it's accepting a pair of electrons. So that's why it's a Lewis acid. So a Lewis acid is something that can accept a pair of electrons, and a Lewis base is a chemical that donates a pair of electrons. Okay? And that's all we're going to say about those. Okay, sorry about that. Couldn't get the slide to move. So one little thing that I want to point out here, and this is kind of, sometimes we use shorthand. So that goes back to that first definition of acids where it's something that releases a proton. So in biology, this is probably what we would say. Nitric acid, put it in water, it's going to release protons and nitrate ions. Chemists, however, really want to know what the exact reaction is. And so this is happening in water. So it's not happening really on its own. Remember, our Bronsted-Lowry acids and bases are occurring in pairs. So really what's happening is the nitric acid is donating a proton to the water, all right? And that's where we're getting our hydronium ion and our nitric ion, okay? So just so you keep that in mind, sometimes we'll use just the H plus as a shortcut, but what we usually mean is it's a hydronium ion. All right, so what does this mean about pH? So we can talk about the concentrations. And so for instance, here are two equations up here. And so one thing I want to point out is look at the role of water in each of these. So in the first reaction, water accepts a proton. So this actually makes it, So this actually makes it a base, okay, because it's accepting a proton. But here in the second reaction, the water is actually going to donate a proton. So here we have CH3OH. So in this case, the water is going to act as an acid. Okay, so water can actually do both. And so we sometimes refer to that as an amphoteric substance. So like an amphibian can live both on land and water. Amphoteric substance can do both. And in fact, if you just have pure water, what happens is that a small amount becomes hydronium and hydroxide ions, a very small amount, and we call that the self-ionization of water, all right? And so if we think about what's happening here, in pure water, remember I said there's those really small amounts? So if we look at the concentration, and these brackets just mean the concentration, if we look at the concentration of these ions, right, if we multiply them together, we get 1 times 10 to the minus 14. So think about what that means, 0.00000, right, 14 times. And since in pure water these two have to be equal, that means the concentration of our hydronium is going to be 1 times 10 to the minus 7. So that's still pretty small, 0.0000001, I think. Okay? All right, so that's kind of awkward to talk about. So a lot of times we'll talk about the pH. And the pH is defined as the negative log of the hydronium ion concentration. Okay, so if we go back to our water, and remember we said the hydronium concentration in pure water is 1 times 10 to the minus 7. If you take the negative log of that, you get 7. Notice the 7 and the 7. All right. And so what this means is when we think about pH in a neutral solution where these two are equal, we get this concentration, we get a pH of 7. In acidic solutions, now we have more protons or more hydronium ions. So we have higher proton concentration. That means this number here is actually going to be, the absolute value is going to be less. So like 10 to the minus 6 is higher than 10 to the minus 7. So that means more hydrogen ions, lower pH. Okay? And the opposite holds true for base. So basic solutions have less hydrogen ions, but more higher pH. So the take-home message here is acids have a pH lower than 7, bases have a pH higher than 7. Okay? All right, and here are some values of some common things. So human blood is neutral, slightly basic actually. Lemon juice has citric acid in it. Ammonia and bleach, a lot of cleaners tend to be basic. We'll do a little activity next week that goes into that a little bit more. And I just want to go over a little bit with pH problems. I'm not actually going to have you do too many of these. But let's say you were given a concentration of an acid. How would you figure out the pH? Well, you know pH is the negative log. So you just take the negative log of 4.5 times 10 to the minus 3, and you should get pH of 2.3. All right, you can do the opposite though. What if you're given a pH value and you want to find out the concentration? All right, so now you have to do a little fancy math because you have to figure out how to get the log of what this would be. So basically you invert it by taking 10 to the x of each side, and then you have to hit that 10 to the x key on your calculator. And in this case, you get 2.1 times 10 to the minus 5. Okay? All right, and then just so you know, I'm not going to go into them, but there are other P scales. So P just means minus log of that concentration. So you could have the POH, and notice this would be the opposite of the pH. So the POH and the pH are going to add up to that 14 number. And then the KW, we're not going to get into that. That's just how the products and reactants balance out. All right. And then we can also classify acids and bases basically as strong or weak. So a strong acid like HCl completely dissociates. So if you put HCl in water, you get pretty much all ionized. All right. So once HCl is in water, there's literally none of like the HCl as a compound anymore. It's all ionized. So that's a strong acid. But a lot of acids, you'll notice this double arrow. That means the reaction's going both ways. So you have a little bit of reactants and a little bit of products. And depending on how this, what this balance is, gives you the pH. And the same thing holds true for bases. All right, so how do we measure pH? And again, you've probably already done this. So you've probably used litmus paper or maybe pH paper that has a certain range. So you can use that. If you want to be more precise, you can use a pH meter. So we actually would have done this if we would have been in class. But basically, since this measures the voltage, remember way back in that second slide, acids and bases can conduct electricity. So you can use that to then convert it to a pH. And that's the basis of how you measure pH. Okay, so I think that's it. As I said, we'll do a little activity for pH next week, and we'll actually get to Zoom. So I apologize for no Zooms this week. And 2 classes next week, and then we're done. All right, see you later.